The largest void ever found is so empty it should not exist. Tonight, I want to walk you to a place where there is, almost literally, nothing. It is one of the largest confirmed voids ever found in the universe, nearly 2 billion light-years across, and the matter inside it is so sparse, so spread out, so close to absent, that it strains the simplest version of our standard model of how the universe should be structured. It is too big. It is too empty. It sits near the edge of what our simulations comfortably produce. Get comfortable wherever you are. Pull something warm close. Let the lights drop a little. We have a long, slow walk ahead. Now, let's begin. Before I tell you about the void, I have to tell you about the universe it is missing from. The universe, on the largest scales we can measure, has a structure. It is not a uniform soup of stars. It is not even a uniform soup of galaxies. The galaxies cluster. They form long, thin filaments of light that stretch across hundreds of millions of light-years, and where the filaments meet, they form denser knots called superclusters, places where dozens or hundreds of galaxies are gathered together by gravity into what astronomers sometimes call cities of galaxies. Between the filaments, there's mostly empty space, and those empty regions are the cosmic voids. If you could see the universe from far enough away, the way you can see a city from an airplane at night, you would not see a smooth field of light. You would see a kind of network, bright threads, glowing knots, vast dark regions in between. Astronomers, when they first started mapping galaxy distributions in the 1970s and 1980s, were surprised by this. They had assumed, on the basis of what is called the cosmological principle, that the universe on large scales should look roughly the same in every direction, with galaxies scattered evenly throughout. The cosmological principle is one of the foundational assumptions of modern cosmology. It is the reason equations like Einstein's field equations can be applied to the universe as a whole. It says that there is no special place. The universe is, on average, the same everywhere. The first redshift surveys, the surveys that mapped the three-dimensional positions of galaxies by measuring how much their light was stretched by the expansion of the universe, started revealing something different. In 1986, Margaret Geller, John Huckra, and Valerie de Lapparent at the Center for Astrophysics published a slice through the local universe, mapping galaxies out to about 600 million light-years in a particular direction. The map showed something that looked, in a way nobody had quite expected, like the inside of a sponge. Galaxies were arrayed along sheets and filaments. Between the sheets were enormous cavities where almost no galaxies were found. The map was so striking that it was reproduced in textbooks within a few years, and it changed the way cosmologists thought about the structure of the universe at large scales. The Center for Astrophysics survey, when it was first published, had a particular feature that became famous on its own. There was, running through the slice of sky they had mapped, a long thin sheet of galaxies that became known as the Great Wall. The Great Wall was about 500 million light-years long, perhaps 200 million light-years wide, and only about 15 million light-years thick. It was the largest single coherent structure of galaxies that had been mapped at the time. Below it, on the other side of a large gap, was another wall. Between the walls, mostly empty space. The picture, when you saw it, was unmistakable. The universe was not smooth. It was structured in a way that was beautiful and entirely new to the science. What the surveys found was that this is true, but only on enormous scales, scales of billions of light-years. On smaller scales, hundreds of millions of light-years, the universe is intensely structured. It has filaments, walls, knots, and most strikingly, it has voids. A void in cosmology is a region of space where the density of matter is significantly lower than the average density of the universe. It is not literally empty. There's still some galaxies inside, scattered very thinly. There is still some interstellar gas, some dark matter, some background radiation. But compared to the dense filaments around it, a void is a place where almost nothing is. Voids are predicted by our standard model of how the universe formed. We expect them to exist. The cosmic web of filaments and voids is a natural consequence of how matter has clumped together over billions of years under the influence of gravity, starting from tiny variations in density that we can still see imprinted on the cosmic microwave background, the leftover radiation from the early universe. The way the cosmic web grew is itself a beautiful piece of physics. In the very early universe, the matter was almost perfectly uniform, but not quite. There were tiny variations in density, of order 1 part in 100,000, the result of quantum fluctuations during the very first fractions of a second. These tiny variations, stretched and amplified by cosmic expansion, became the seeds of all later structure. Wherever the density was a little higher than average, gravity pulled in more matter, and the region got denser still. Wherever the density was a little lower, matter drifted out toward the denser regions, and the region got emptier. Over billions of years, this slow gravitational sorting turned the smooth early universe into the cosmic web we see today. The voids are not failures of structure. They are the regions from which matter has been pulled away, leaving a deficit behind. There is something almost narrative about this picture. The universe, in its first moments, contained everything in roughly equal amounts. Then, very slowly, the rich got richer and the poor got poorer. The denser regions accumulated more matter, gathering it from the surroundings. The less dense regions gave up their matter, becoming emptier. After 13 billion years of this slow gravitational sorting, the cosmos has separated itself into the bright places, where galaxies live, and the dark places, between them, where almost nothing remains. Both kinds of places are part of the same story. They are two sides of the same gravitational evolution. So when I tell you that there is a region of space where there is almost nothing, I am not telling you that physics is broken. The presence of voids is expected. The cosmic web is real and well understood in its general shape. What is not expected, and what is the strange story I want to walk you through tonight, is the size and depth of certain particular voids. Some of them are bigger than they should be. Some of them are emptier than the standard model of cosmology predicts they should be. And the largest one we have ever found, the one I will get to in detail in a few minutes, is the most extreme example of all of them. That is the spirit of the title. Voids are supposed to exist. This one is strange because of how large it is, how empty it is, and what it might be connected to. Hold that thought. We're going to keep coming back to it. Before we go further, I want to give you a clearer picture of what a cosmic void looks like. Imagine the universe as a slice of bread. Not a smooth slice, but a slice with holes in it. The kind of artisan loaf where the dough has bubbled up during baking and left large empty pockets surrounded by the denser, more crusty crumb. The crumb is the cosmic web. The bubbles are the voids. The bubbles are not perfectly spherical. They are irregular. They are different sizes. They are sometimes connected to each other. But they are real. They are emptier than the surrounding crumb, and they take up most of the volume of the universe. That last point is the one that surprises people. Voids are not rare features in a mostly full universe. Voids are most of the universe, by volume. The bright filaments, the clusters, the knots of galaxies that we tend to think of as the universe, are actually just the thin walls between vast emptier regions. If you measured the universe by how much space is taken up by stuff, the answer is that very little space is taken up by stuff. Most of it is taken up by gaps. The smallest voids are tens of millions of light-years across. The medium ones are around 100 million light-years across. The supervoids, the largest ones, can be many hundreds of millions of light-years across, and a few are larger still. Voids are not completely empty. Inside a typical void, you might find a small number of galaxies, scattered very thinly. The galaxies inside voids tend to be different from the galaxies in dense regions. They are often smaller. They tend to be bluer, suggesting more recent star formation. They are sometimes called void galaxies, and studying them has become its own subfield of astronomy, because they tell us about how galaxies evolve when they are far from neighbors and have access to less material. The space between the void galaxies is mostly extremely thin gas, far thinner even than the average density of the intergalactic medium outside the void. There is dark matter, but less of it than the cosmic average. There are photons from the cosmic microwave background, but those are everywhere, and that is essentially all. You could fly through a typical void at the speed of light for 100 million years and pass nothing. No stars, no gas clouds, no planets, just darkness, with the dim glow of distant filaments visible in the far distance, on either side, like the lights of a coastline visible from far out at sea. That is the texture of nothing, on a cosmic scale. Not absolute emptiness, but emptiness so dilute that the difference is almost meaningless to any human sense of distance. And the largest one we have found is the place we are walking toward tonight. To understand why some voids are strange, you have to understand the rule they are bending. The cosmological principle is one of the most important assumptions in modern physics, and it is one of those assumptions that we make so habitually that we almost forget we are making it. The principle says that the universe, on sufficiently large scales, is homogeneous and isotropic. Homogeneous means that the average density of matter is the same everywhere. Isotropic means that the universe looks the same in every direction. There's no center. There's no edge. There's no special place. Wherever you are, and whichever way you face, the universe looks, on average, the same. This sounds like a metaphysical claim, but in practice it is a working assumption that lets cosmology be a science at all. Without it, you cannot apply equations like Einstein's general relativity to the universe as a whole. Without it, every region of space might have its own physics, its own history, its own behavior. With it, you can make predictions. You can compute. You can model. The principle is not exactly true. We can see, just by looking up, that the universe is not perfectly uniform. There are stars and galaxies in clusters in some places, and almost nothing in others. The principle has always been understood as an approximation, true only on scales large enough that the local clumping averages out. The question is, on what scale does the averaging actually work? The standard answer, until quite recently, has been that the universe becomes effectively uniform somewhere around 250 to 300 million light-years. On smaller scales, you see structure. On larger scales, the variations smooth out. This number is called the scale of homogeneity, and the standard model of cosmology depends on it. What the discovery of supervoids has been doing slowly, over the last several decades, is challenging that number. If a void is 200 million light-years across, that is at the upper edge of normal structure. If a void is 500 million light-years across, that is starting to push past the scale at which the universe is supposed to be homogeneous. And if a void is over 1 billion light-years across, that is genuinely difficult to fit into the standard picture. Either the scale of homogeneity is larger than we thought, in which case the cosmological principle is much weaker than the standard model assumes, or there is something specific about the way these voids form that the standard model is missing. That is the broader puzzle. Each individual giant void is, on its own, unusual. The pattern of finding more and more of them, getting larger and larger, is the deeper concern. We are about to walk through that pattern. The first one I want to take you to is the one that started it. In 1981, an American astronomer named Robert Kirshner was working on a redshift survey of the constellation Boötes. The constellation is in the northern sky, in the region where the Big Dipper points if you trace its handle outward. Kirshner and his collaborators were measuring the distances to galaxies in that direction by looking at how much their light had been stretched, redshifted, by the expansion of the universe. The redshift gave them the distance. The distance, combined with the position in the sky, gave them a three-dimensional map of where the galaxies were. The technique sounds straightforward, but was not. In 1981, the technology of redshift surveys was still relatively young. Each galaxy required a separate observation. Each observation required a telescope with a spectrograph, careful calibration, and patient analysis to extract the redshift from the light. A survey of even a few hundred galaxies represented hundreds of hours of telescope time. Kirshner's team was working with telescopes available at the time, building up a catalog one galaxy at a time, plotting each new measurement on a slowly developing three-dimensional map of the local universe. What they found, in the data, was a region of space where there were almost no galaxies at all. The region was roughly spherical, about 250 to 330 million light-years across, depending on how you measured the boundaries. Inside it, there were perhaps 60 galaxies. For a region that size, in a typical part of the universe, the expected number of galaxies would have been around 2,000. The team double-checked. They expanded the survey. They looked from other angles. The result held. There was a region of space, in the direction of Boötes, where almost nothing was. They called it the Boötes Void. Other astronomers, in informal conversation, started calling it the Great Nothing. Kirshner himself, in a quote that has become famous in cosmology, once said that if the Milky Way had been at the center of the Boötes Void, we would not have known there were other galaxies in the universe until the 1960s. That is how empty it is. From inside it, looking out, the rest of the universe would be too far away, too distant, too sparse, to have been detected by any telescope before the era of large optical surveys. This was a genuine surprise to cosmologists at the time. Voids were known to exist, but the Boötes Void was much larger and emptier than anyone had expected. It was too big. It was too empty. The standard models of structure formation that existed in 1981 had a hard time producing voids of that size. Over the next 40 years, follow-up surveys filled in some of the gaps. The Boötes Void was found to contain a few more galaxies than the original survey detected. The galaxies inside it, when studied in detail, turned out to be slightly bluer and slightly more star-forming than typical galaxies, consistent with what we would expect for galaxies in low-density environments. Some cosmologists have argued that the Boötes Void might not be a single void at all, but a few overlapping voids that, viewed from our angle, look like one large structure. But even with all of those refinements, the Boötes Void remains one of the strangest objects in the local universe. It is enormous. It is mostly empty. It sits in the data like a hole in a piece of paper, a place where the cosmic web simply isn't. And the strange thing, the genuinely unsettling thing, is that the Boötes Void was only the first one. Once astronomers knew what to look for, they started finding others. And as the surveys got bigger, the new voids got bigger too. The pattern that emerged in the years that followed would slowly reveal something that nobody in 1981 had been prepared to see. I want to spend a moment letting that number sink in, because it is the kind of number that is easy to read and hard to feel. A void 330 million light-years across with 60 galaxies in it. The Milky Way alone, our home galaxy, contains somewhere between 100 and 400 billion stars. The local group, the small cluster of galaxies in our immediate neighborhood, contains about 80 known galaxies of various sizes, packed into a region about 10 million light-years across. The Virgo supercluster, the larger structure that includes our local group, contains thousands of galaxies in a region about 110 million light-years across. The cosmic web is dense in our part of the universe. Now imagine a sphere, 3 times the diameter of the Virgo supercluster, with about 60 galaxies in it. Not 60 trillion, not 60 million, 60. Let me try to make that more concrete. A typical galaxy contains 100 billion stars. 60 galaxies, taken together, might contain 6 trillion stars. That sounds like a lot, but spread those stars across a region 330 million light-years wide, and you get a star density so low that the average distance between stars is, in any practical sense, beyond comprehension. In our solar neighborhood, the average distance between stars is about 4 light-years. In the densest part of the Boötes Void, between the few galaxies that exist there, the typical distance from one star to the next nearest star, in any galaxy, would be measured in millions of light-years. The sky from a planet inside the Boötes Void, even at its densest, would be staggeringly empty. If you could stand on a planet in one of those 60 galaxies, on a clear night, you would look up and see a darker sky than any human has ever seen from Earth. The familiar smear of the Milky Way would not be there, because there would be no Milky Way nearby. No nearby stars at all in any familiar concentration. The few galaxies that share your void would be too far away to be seen with the naked eye. Even a powerful telescope would show only a few faint smudges, scattered across an otherwise empty sky. Beyond those, there would be the light of the rest of the universe, but it would be far away, on the other side of an enormous expanse of nearly empty space, faint and remote. It would look like the universe had ended just outside your galaxy. That is the texture of life, if there is any, inside the Boötes Void. That is the kind of place we are talking about when we say the cosmic web has gaps. And there is something quietly philosophical about that emptiness, too. Any civilization that arose inside a void like Boötes would, for most of its history, have no evidence that other galaxies existed at all. They would believe the universe was much smaller than it actually is. They would have to wait for technology good enough to detect distant smudges in the dark before they could even begin to suspect that the cosmos extends far beyond what they could see. And the Boötes Void, despite all the attention it has received, is not even close to the largest one we have found. In 1988, 7 years after Kirshner's discovery, another large underdensity was found in the constellation Canes Venatici, the hunting dogs. It was discovered by a different team using different techniques, and it turned out to be larger than the Boötes Void by a substantial margin. The estimated diameter of this new void was somewhere between 1 billion and 1.3 billion light-years, with its center about 1.5 billion light-years from Earth. It was given the unimaginative name Giant Void, sometimes called the Canes Venatici Supervoid. The Giant Void was, for a while, the largest cosmic void on record. It contains some galaxy clusters, more than the Boötes Void does, but they are clustered in a small spherical region inside the larger void, and the rest of the volume is mostly empty. The clusters do not interact with each other much, gravitationally, because the overall density is so low. They drift, more or less, on their own. When the Giant Void was announced, it was largely received with the same kind of mixture of excitement and skepticism that had greeted the Boötes Void. Some cosmologists pushed back, arguing that the void was an artifact of incomplete surveys, or that it was overlapping voids being measured as one. Others took the discovery seriously and started asking whether the standard model of cosmology was capable of producing voids that big. Over the following decades, more giant voids kept turning up. Some of them were close to home. Others were far away. Each one stretched the limits of what the standard model expected. By the early 2000s, cosmologists had started to suspect that the universe might have more giant voids than the standard model predicted. The pattern was suggestive. The handful of identified supervoids were all bigger than expected, all emptier than expected, and all challenging the assumed scale of homogeneity. There was no single discovery that broke the model, but the cumulative effect of finding so many large voids was creating quiet pressure on the cosmological framework. And then, in the 2010s, the team behind the Dark Energy Survey started looking, in detail, at a particular cold patch in the cosmic microwave background. The patch had been known about for years. It had been one of the unsolved puzzles of modern cosmology, and the question they were asking was simple. Could a giant void, larger than any previously known, be hiding in the same direction as the cold patch? If it was, that would be the largest void anyone had ever found. To understand what comes next, I need to walk you through one of the most remarkable measurements in the history of cosmology. The cosmic microwave background, often shortened to the CMB, is the leftover radiation from the early universe. It is the light that was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and for photons to travel freely for the first time. That ancient light has been traveling through space for almost 14 billion years, getting stretched along the way by the expansion of the universe, until today we detect it as a faint glow of microwave radiation coming from every direction in the sky. The CMB is, in many ways, our best window into the early universe. The pattern of tiny temperature variations in the CMB, of order 1 part in 100,000, encodes information about the matter, energy, and geometry of the universe at the moment that radiation was released. By measuring those variations precisely, cosmologists can extract numbers like the age of the universe, the density of dark matter, the rate of expansion, and many other fundamental properties. The first satellite to map the CMB in detail was COBE in the early 1990s. It found the basic temperature variations and showed that they matched the predictions of the standard model. The next satellite was WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001, which produced a much higher resolution map. After WMAP came Planck, a European satellite launched in 2009, which produced the most detailed map of the CMB we have, and which has since become the gold standard for cosmological measurements. When the WMAP team published their first detailed map in 2004, they noticed something odd. In a particular region of the sky, in the direction of the constellation Eridanus in the southern hemisphere, there was a patch where the temperature of the CMB was anomalously cold. Not by a huge amount, in absolute terms. We are talking about variations on the order of microkelvin. But statistically, The patch was significantly colder than the standard model of cosmology predicted any single region should be. The patch was several degrees of arc across, the size of a fist held at arm's length, and its temperature was about 70 microkelvin colder than the average CMB temperature. It was named the CMB cold spot. Let me put the temperature in human terms. The CMB itself is about 2.725 degrees above absolute zero, which is to say, about minus 270 degrees Celsius, vanishingly cold. The temperature variations across the sky are, on average, on the scale of a few tens of microkelvin. A microkelvin is 1/1,000,000th of a degree. The cold spot is about 70 microkelvin colder than the surrounding CMB. That is, in absolute terms, a tiny temperature difference. It is a difference so small that no thermometer in any laboratory on Earth could measure it. The instruments on satellites that detect it have been designed and refined over decades to be sensitive to differences this small. But the smallness is not what made the cold spot interesting. What made it interesting was the size of the patch. In the sky, that was anomalously cold. A small region of slightly colder than average CMB would be entirely expected from the random fluctuations of the early universe. A large region of consistently colder than average CMB, of the size of the cold spot, is much harder to explain that way. The probability of finding a coherent cold patch of that size and depth, by chance, in the standard model, is small. It is not zero, but it is small enough that astronomers started to suspect there might be a physical cause beyond random chance. The standard model of cosmology, with all its successes, did not have a clean explanation for it. The variations in the CMB are supposed to be random, the result of quantum fluctuations in the very early universe stretched out by inflation to cosmic scales. A patch as cold as the cold spot is supposed to be rare. Statistically, you would expect to find one of comparable size and depth somewhere in the sky. But the question is whether the standard model can account for it on its own, or whether something else, something larger and stranger, is involved. When Planck released its even more detailed map of the CMB in the 2010s, the cold spot was confirmed. It was not an artifact of the WMAP instrument. It was real. There was, genuinely, a colder than expected patch in the leftover light of the early universe, in a particular direction in the southern sky. The question was what could be making it cold, and the answer, when it came, would turn out to be the largest object anyone had ever found in the universe. In the years after the cold spot was confirmed, several groups of astronomers started looking for what might be in the line of sight to it. The reasoning was simple. If something between us and the surface from which the CMB was released was cooling the photons as they traveled toward us, that something would have to be in the direction of the cold spot. And one of the natural candidates was a very large supervoid. The team behind the Dark Energy Survey, working with a powerful telescope at the Cerro Tololo Inter-American Observatory in Chile, began mapping the distribution of matter in the direction of the cold spot in detail. They were using a technique called weak gravitational lensing, in which the slight bending of light from distant galaxies by foreground matter is measured to map the matter distribution, including the dark matter, even when the matter itself is invisible. What they found, and reported in a series of papers culminating in 2021, was that there is, in the direction of the cold spot, a genuinely enormous underdensity in the distribution of matter. The structure is elongated, stretched out along the line of sight. It is about 1.8 billion light-years wide. Its center is about 2 billion light-years from Earth. The matter density inside it is about 30% lower than the average density of the universe. They named it the Eridanus Supervoid, after the constellation in which it sits. It is, by the most direct measurement we have, one of the largest single underdensities of matter ever confirmed in our observable universe, and the strongest candidate for the largest confirmed underdensity we have mapped. Let me put those numbers in human terms. A region 1.8 billion light-years wide is so large that light, which travels at the fastest speed allowed by physics, takes nearly 2 billion years to cross it. The light entering the Eridanus supervoid from one side will not reach the other side until almost twice the lifetime of multicellular life on Earth has passed. The supervoid is bigger, by a factor of several, than the Boötes Void, which itself was already considered extreme. It is bigger than the giant void of Cain's Venatici. It is, by every measurement we have, a structure of a different order of magnitude than the typical voids that the cosmic web is supposed to contain. To put it another way, the Eridanus Supervoid is enormous compared with the scale on which the universe is supposed to smooth out into uniformity. It is not a large fraction of the entire observable universe, which has a radius of about 46 billion light-years, but it is many times larger than the scale of homogeneity that the Standard Model assumes, the scale at which local clumping is supposed to average out. It sits in our universe in a single direction, like a hole punched through a sheet of paper, except the sheet of paper is the visible matter distribution of everything we can see, and inside it, the average matter density is 30% below the cosmic mean. That number does not sound enormous in isolation, but for a region 1.8 billion light-years wide, it represents an absolutely staggering deficit of matter. There are missing galaxies, missing dark matter, missing gas, missing everything, on a scale that is hard to picture even for people who think about cosmology for a living. To get a sense of the deficit, imagine taking 30% of all the matter in a sphere 2 billion light-years across and removing it from the universe. That is approximately what the Eridanus Supervoid represents. Not zero matter, not absolute emptiness, but a 30% shortfall, distributed across a region so vast that even at the speed of light, you could not traverse it in less than the time it took multicellular life on Earth to evolve from single cells to whales. The discovery of the Eridanus Supervoid, in this size and shape, created a new conversation in cosmology, because if a void this large can exist, then the Standard Model has work to do. The cosmological principle says that on sufficiently large scales, the universe should be uniform. The Eridanus Supervoid is on those scales, and it is not uniform. I want to tell you a little more about the shape of the Eridanus Supervoid, because the shape itself is part of the story. The Eridanus Supervoid is not spherical. It is elongated. The technical word in the literature is cigar-shaped, although that word makes the structure sound smaller than it is. The supervoid is stretched out along our line of sight, extending much farther in the radial direction, the direction away from us, than it does perpendicular to that line. The transverse radius is something like 600 to 650 million light-years. The radial extent is much larger, possibly twice that or more. This shape is unusual, but it is not unprecedented. Other large structures in the universe also have elongated forms, stretched along particular directions for reasons that are not always fully understood. The reason it matters here is that the elongation increases the effect the void can have on light passing through it. If a void is larger in the radial direction, photons traveling toward us spend more time inside it, and the cumulative effect on their energy is correspondingly larger. There's also a question of why the void is shaped this way at all. The Standard Model of structure formation does not have a clean explanation for why supervoids should be elongated rather than spherical. In simulations, voids tend to be roughly spherical or moderately ellipsoidal, with the kind of irregular shapes that you would expect from random gravitational evolution. A void as elongated as the Eridanus Supervoid is, again, at the edge of what the standard simulations comfortably produce. It is possible that the elongation is an artifact of how we are measuring the structure, that the line of sight extent is harder to pin down precisely than the perpendicular extent, and that the true shape is closer to spherical than the data currently suggest. But it is also possible that the elongation is real, and that whatever process produced this supervoid had a directional component that the Standard Model does not currently capture. That brings us to the question of how, exactly, the Eridanus Supervoid might be connected to the cold spot. The mechanism that has been proposed, and that fits the data best, is called the Integrated Sachs-Wolf Effect, or ISW for short. It is a real, predicted, and measured effect of general relativity in an expanding universe. The effect, in simplified form, says this: when a photon travels through a region of lower matter density, it loses a tiny bit of energy on the way out, because it has to climb out of a slightly shallower gravitational well than it fell into. The energy loss shows up as a tiny cooling of the photon's wavelength. When a photon passes through an underdense region in an accelerating universe, where the gravitational well is shallowing over time, the cooling effect is enhanced. A photon traveling from the early universe to our telescope, passing through the Eridanus Supervoid on the way, would lose a measurable amount of energy compared to a photon passing through an average region. That energy loss would show up on our detectors as a cold patch in the CMB. I want to be careful with how I phrase this next part, because the science is genuinely strong, but not fully settled. The integrated Sachs-Wolf effect from a void as large as the Eridanus Supervoid is real, and it does predict some cooling of the CMB in that direction. The question is whether the predicted amount of cooling is enough to fully explain the depth of the cold spot. The most recent analyses suggest it might be a substantial part of the explanation, but probably not the entire explanation. Some additional cooling, possibly from a primordial fluctuation in the early universe, may also be involved. What is fair to say is this: the Eridanus Supervoid is real. The CMB cold spot is real. The two are aligned in the same direction in the sky. And the supervoid is large enough and deep enough that it almost certainly contributes to the coldness of the patch, even if the full explanation is more complicated. That alone is one of the most remarkable findings in modern cosmology. One of the largest empty regions we have ever identified is sitting in the same direction as one of the strangest anomalies in the cosmic microwave background, and the geometry suggests they are physically connected. I want to spend another moment on the integrated Sachs-Wolf effect, because it is one of the most beautiful pieces of physics in this whole story, and it deserves a careful explanation. Imagine you are at the bottom of a hill. To get out of a valley, you have to walk uphill, expending energy. By the time you reach the top, you have less energy than you started with, because some of it went into climbing. Now imagine you are at the top of a hill, walking down into a valley. You gain energy on the way down. You exit the valley with more kinetic energy than you started with. If the valley is unchanged in depth from when you entered it to when you leave it, the energy you gain going in is exactly equal to the energy you lose coming out, and you exit with the same amount of energy you started with. The hill takes nothing from you on net. That is what photons would do, on average, if they passed through gravitational potential wells in a static universe. They would gain energy falling into the well, lose it climbing out, and exit unchanged. But the universe is not static. The universe is expanding, and the rate of expansion is accelerating because of dark energy. As the universe expands, gravitational potentials evolve over time. A void, which is a region with less matter and therefore a shallower gravitational well, gets shallower still as the universe expands and the matter inside it spreads out. A photon traveling through an evolving void in an accelerating universe does not gain back what it lost. It enters the shallow well, falls in slightly, gains a tiny bit of energy. By the time it has crossed the well and is climbing out the other side, the well has become even shallower than it was when it entered. So the photon climbs out of a shallower hill than it fell into, and it loses, on net, a small amount of energy. That energy loss is the integrated Sachs-Wolf effect. It is small in absolute terms. The cumulative cooling from passing through a typical void is just a few microkelvin. But across a void as large as the Eridanus Supervoid, the cumulative effect is significant. It can add up to tens of microkelvin of cooling, possibly more, depending on the depth and shape of the void. The cold spot is about 70 microkelvin colder than the average CMB temperature. The integrated Sachs-Wolf effect from the Eridanus Supervoid, by most modern estimates, accounts for somewhere between a third and most of that, depending on the exact model of the void structure. The remaining cooling, if it exists, would have to come from somewhere else, and one of the leading candidates is that the cold spot also has an underlying primordial component, a particularly large quantum fluctuation that happened to land in that direction in the early universe and was stretched by inflation into the patch we see today. So the cold spot might be a story of two effects: a large primordial fluctuation from the very beginning, plus a giant void closer to us amplifying the cooling through the integrated Sachs-Wolf effect. Both of them lined up in the same direction, both contributing to the coldness we see. That is the current best picture, and it is the kind of picture that, if you sit with it for a moment, is genuinely strange. We are looking, in that direction, at the combined imprint of one of the largest empty regions we have ever found and a primordial echo of the early universe, both visible in the same patch of sky. This is also, by the way, a good place to mention something that makes this whole story even harder to navigate. We are not just looking at the universe from outside. We are part of it, and the part of the universe we live in turns out to have its own strange property, one that we have only recently begun to take seriously. We may be sitting inside a void of our own, and if we are, almost everything we have ever measured about the universe might need to be reconsidered. In 2013, 3 astronomers named Ryan Keenan, Amy Barger, and Lennox Cowie published a paper that changed the way many cosmologists think about our local part of the universe. They had been counting galaxies in the near-infrared, looking at how the average density of galaxies changes as you move outward from the Milky Way. The expectation, based on a cosmological principle, was that the local density should match the average density of the universe pretty closely once you got out to a few 100 million light-years. Local fluctuations are normal, but on those scales, the density should average out. What they found was different. Out to about 300 megaparsecs, a billion light-years, the average density of galaxies in our part of the universe is about 30% lower than the cosmic average. We are, in their analysis, sitting inside an underdense region that extends nearly a billion light-years in every direction. This region, when later workers refined the analysis, became known as the Keenan-Barger-Cowie void, or KBC void for short. It has also been called the local hole, because it is, essentially, a hole in the cosmic distribution of matter, and we are at the bottom of it. The KBC void is large. It is significantly larger than the Boötes Void. It is somewhat smaller than the Eridanus Supervoid, but it is notably deeper in some analyses, and it is, crucially, the void that we live in. Imagine the surprise of that discovery. For most of the modern era of cosmology, we have assumed that our location in the universe is typical. The cosmological principle would suggest that we are not in any special place, but the data, as we accumulate more of it, are starting to suggest that we might in fact be in a slightly unusual place. We might be at the bottom of an enormous hole in the matter distribution, looking out at a universe that is, on average, denser than our immediate surroundings. This idea, when you sit with it, has a strange double quality. On the one hand, it is humbling. We are not, in this picture, in a typical part of cosmos. We are in a particularly empty corner of it, the neighborhood that has felt, throughout the history of human astronomy, like the universe itself, is in fact a kind of low-density alcove within a denser, surrounding cosmos. The galaxies and clusters we have spent decades cataloging are, in this picture, the sparse population of a hole in the cosmic web. On the other hand, it is also, in a way, fitting. The galaxies inside voids tend to evolve more slowly. They tend to be smaller, bluer, less interactive with neighbors. If our region is genuinely an underdensity, that might explain why our local galactic environment is what it is. We are in a quieter neighborhood than the cosmic average, and that has shaped what our part of the universe looks like. This is not, in itself, a violation of any law of physics. Voids exist. Some regions are emptier than others. We could happen to live in one, just as somebody, statistically, has to live somewhere. But the size and depth of the KBC void are pushing what the standard model is comfortable predicting. Voids of that size are not common in standard simulations of structure formation. Finding ourselves in one is unexpected, and the existence of such a structure adds to the broader pattern of supervoids that the standard model has trouble explaining. There's also a more practical consequence. If we are inside a void, then our local measurements of the universe are not perfectly representative of the universe as a whole. The measurements we make from inside a void will be slightly distorted by the fact that we are looking out from an underdense region. And one particular measurement, in particular, has been the subject of a major controversy in recent years. That measurement is the rate at which the universe is expanding. I want to introduce, in this section, one of the most discussed and most stubborn problems in current cosmology. The Hubble constant is the number that tells us how fast the universe is expanding. It is named after Edwin Hubble, who in the 1920s discovered that distant galaxies are moving away from us, and that the further away they are, the faster they are receding. The constant of proportionality between distance and recession velocity is the Hubble constant. It is one of the most important numbers in cosmology because it directly determines the age of the universe, the size of the observable universe, and many other fundamental quantities. There are two main ways to measure the Hubble constant. The first is to look at the early universe, using the cosmic microwave background, and infer what the expansion rate must be to produce the patterns we see. This gives one number. The second is to look at the local universe, using observations of supernovae and other distance indicators, and measured directly how fast nearby galaxies are receding. This gives another number. The two numbers do not agree. The CMB-based measurement gives a Hubble constant of about 67 to 68 kilometers per second per megaparsec. The local measurement gives a value of about 73 kilometers per second per megaparsec. The disagreement is more than 5 sigma, which in statistical terms means it is extremely unlikely to be a chance fluctuation in the data. Both measurements have been refined and rechecked many times. Both seem to be correct, in the sense that they are giving genuinely different values. The disagreement is real. To understand how strange this is, you have to understand how good these measurements are. The CMB measurement uses data from the Planck satellite, which mapped the temperature variations of the cosmic microwave background with extraordinary precision. The team applied the standard cosmological model to those measurements and extracted, among many other quantities, the Hubble constant. The result has been refined and reconfirmed by multiple independent analyses, all using the same Planck data, and they agree with each other. The local measurement uses the cosmic distance ladder, a layered series of distance estimates anchored on nearby objects with known distances and extending outward to galaxies far enough away that their recession velocities dominate over local motion. The most prominent group doing this work, led by Adam Rees at Johns Hopkins University, has been refining the local measurement for years. Their result has also been confirmed by independent methods, including measurements based on red giant stars, gravitational waves from neutron star mergers, and other completely separate techniques. So we have two measurements, made with different techniques, anchored in different parts of the universe, both refined to high precision, and they disagree by more than 5 sigma. The disagreement is one of the most important unresolved problems in cosmology today. This problem is called the Hubble tension. It has been one of the most actively studied issues in cosmology over the last decade. There are many proposed explanations, including modifications to the laws of physics in the very early universe, additional kinds of relativistic particles, exotic forms of dark energy, and various other possibilities. Most of these explanations require new physics that we do not currently have direct evidence for. One possible explanation, and the one that is relevant to the story we are telling tonight, is much simpler. If we live in a large underdense region, the KBC void, then our local measurements of the expansion rate would be slightly biased. Galaxies just outside the void would appear to be receding faster than they actually are, because the void itself would have a kind of outflow pattern, with matter on the edges being drawn outward toward the denser surrounding regions. From inside, this outflow looks like an enhanced local expansion rate. We would measure a Hubble constant that is locally larger than the average for the universe as a whole. Some calculations suggest that a void with the depth and size of the KBC void could account for a significant portion of the Hubble tension, possibly all of it. Other calculations suggest that the void can explain part of the tension, but not the entire effect. The debate is ongoing, and the answer depends on detailed properties of the void that are still being measured. There is also a separate piece of evidence that has emerged in recent years that points in the same direction. Astronomers studying the bulk motions of galaxies, the average velocities at which large groups of galaxies are flowing through space, have found that these flows are larger than the standard model predicts on scales of a few 100 million light-years. Galaxies in our local neighborhood are moving, on average, faster than they would in a perfectly uniform universe. This is exactly what would be expected if we live in a void, with matter being gravitationally pulled outward from the void's interior toward the denser regions surrounding it. The bulk flow data, like the Hubble tension data, is at least consistent with the existence of a substantial local underdensity. A research group led by Eridanus Supervoid and his colleagues has been working on this connection in detail, using semi-analytic models of how a KBC-like void would influence the local expansion rate and the bulk flow of galaxies. They have found that a single underlying structure can explain both anomalies at once. The model is not yet complete, and there are competing analyses that find different results, but the basic story is consistent. A void of the right size, in the right place, with the right depth, can simultaneously explain the Hubble tension and the bulk flow problem, two of the most persistent disagreements between theory and observation in modern cosmology. There is one more piece of context worth mentioning. The KBC void analysis depends on near-infrared galaxy counts, and there has been a long history of disagreement about whether those counts are correctly calibrated. Some studies, using different surveys, have found smaller underdensities or no underdensity at all in the local region. The question is genuinely unsettled. The most recent papers, using the largest galaxy catalogs available, have continued to find evidence consistent with the KBC void, but the size and depth of the void remain uncertain by significant factors. We may live in a deep void, in a shallow void, or in a region of the universe that is mostly average. The data is not yet clean enough to say with confidence which is the case. What is clear is that this is one of the few proposed solutions to the Hubble tension that does not require new physics. If we are in a void, and the void has the properties suggested by the KBC analysis, then the apparent disagreement between the early universe and local measurements of the Hubble constant could be a natural consequence of our local environment, rather than a fundamental problem with the cosmological model. That possibility is one of the reasons cosmologists are paying so much attention to supervoids these days. They are not just curiosities. They might be signs that our standard picture of the universe is incomplete in specific, measurable ways. This is also a good moment, while we are sitting with the strangeness of all this, to mention something I should have brought up earlier. If you have been finding these slow walks through the cosmos worth your time, a quiet subscribe is the simplest way to keep them going. It is a small thing on your end, and a real help on mine. Now back to the story. Voids are not the only scale problem. The opposite side of the problem is giant walls. In 2013, a group of astronomers reported the discovery of an enormous structure in the distribution of gamma-ray bursts, the brief, intense flashes of high-energy radiation that mark the explosive deaths of certain massive stars and the mergers of certain compact objects. The structure they found is called the Hercules Corona Borealis Great Wall, named after the constellations in which it sits. Its claimed extent is roughly 10 billion light-years across, more than two-thirds of the radius of the observable universe. If the structure is real and as large as the analysis suggests, it is far larger than the scale at which the universe is supposed to be homogeneous. The discovery has been challenged. Some analyses argue that the Hercules Corona Borealis Great Wall is a statistical artifact, that the gamma-ray bursts used to identify it are unevenly distributed for reasons that have nothing to do with an underlying physical structure. Other analyses continue to support some kind of large-scale structure in that region, although its exact extent remains uncertain. We do not yet know with full confidence whether the wall is as large as first reported, smaller, or partly an artifact of how gamma-ray bursts are catalogued. What matters for our story tonight is that the broader pattern is consistent on both sides. The voids are bigger and emptier than expected. The walls, if they are real at the reported scale, are larger than expected too. Both sides of the cosmic web, the underdense and the overdense, keep producing structures at scales that the simplest version of the cosmological principle does not comfortably accommodate. There are several possible interpretations. We may be getting the scale of homogeneity wrong, and the universe might be significantly less uniform on large scales than the standard model assumes. The standard model of structure formation may be missing something about dark matter, the early universe, or gravity at very large scales. Or some of these structures may turn out, with better data, to be smaller than current claims suggest. We do not yet know which of these explanations, or which combination of them, is correct. But the question is open in a way it was not open a generation ago. The discovery of giant voids and the apparent presence of giant walls has made it clear that the universe on its largest scales is more structured than the simplest cosmological models would suggest. When you put all of this together, a picture starts to form that is, in its own quiet way, more unsettling than any single discovery would suggest. The universe, on the largest scales we can map, is structured. We knew this. The cosmic web is real, and it has filaments and voids. What we did not fully appreciate, until the last few decades, is that the structure extends to scales that strain our current models. The voids are bigger than expected. They are emptier than expected. The walls and superstructures are larger than the cosmological principle was supposed to allow. We live in one of these voids, possibly. The largest known void is connected to one of the strangest anomalies in the leftover light of the early universe. None of this means the standard model is wrong in the sense of being totally incorrect. The standard model, called the Lambda Cold Dark Matter Model, or LCDM for short, is one of the most successful theories in the history of physics. It correctly predicts the abundance of light elements created in the first few minutes of the universe. It correctly predicts the spectrum of the cosmic microwave background. It correctly predicts the large-scale clustering of galaxies in its broad strokes. It is not a wrong theory, but it might be incomplete. The pattern of giant voids in giant structures suggests that there is something about how matter clumps on the largest scales that the model does not fully capture. The Hubble tension suggests that the model is missing a piece somewhere, either in the early universe or in our local environment. The cold spot in the cosmic microwave background suggests that there are features of the universe at the largest scales that require careful explanation, possibly involving structures we are still discovering. There are speculative proposals at the edges of cosmology that try to make sense of all of this. Some of them involve modifications to gravity at very large scales. Some involve extra components of dark energy or dark matter. Some involve the possibility that what we see as our universe is actually a small bubble within a larger cosmos, and that the giant voids and walls are imprints of collisions or interactions between bubbles. Some involve completely new physics that we have not yet discovered. The bubble collision idea, in particular, is one of the more striking proposals. In some models of cosmic inflation, the very rapid expansion that the universe underwent in its earliest fraction of a second, our observable universe is one of many bubbles of inflation, each one nucleating from a larger, inflating background. Two such bubbles, if they nucleated near each other in the larger landscape, could in principle collide. The collision would leave a signature in the cosmic microwave background, possibly a cold patch or a circular feature. Some cosmologists have wondered whether features like the cold spot could be the imprint of an ancient bubble collision, a kind of cosmic bruise where our bubble brushed up against another one in the very early universe. The proposal is speculative. It does not yet have strong direct evidence supporting it, but it is one of the ways that the unusual features in the CMB might be telling us something about a much larger structure beyond what we can normally observe. Another proposal involves modified gravity. The standard model of cosmology assumes that gravity behaves the same way on all scales, from the local solar system to the largest distances we can measure. Some theorists have suggested that on scales of hundreds of millions or billions of light years, gravity might behave slightly differently than the standard equations predict. If so, the formation of large structures, including supervoids and great walls, might proceed differently than the standard model expects, and the discrepancies we are seeing might be evidence of that modified behavior. Like the bubble collision idea, modified gravity is speculative. There are constraints on how much gravity can deviate from the standard form without contradicting other observations, but it is not ruled out as a possible explanation for the patterns we are seeing. A third proposal involves the dark energy itself. Dark energy, the mysterious component of the universe that is driving the accelerating expansion, is currently modeled as a simple cosmological constant, a uniform energy density throughout space. But it is possible that dark energy has more complicated properties than the simple constant. If it varies in time, or if it interacts with matter in ways that the standard model does not capture, the formation and evolution of voids could be different from what current simulations predict. Some recent analyses, including data from the Dark Energy Spectroscopic Instrument, have tentatively suggested that dark energy might be evolving over time, although the result is not yet definitive. If that turns out to be confirmed, it would have implications for void formation and could potentially help explain the patterns we are seeing. Most of these proposals are, at the moment, untested. They are mathematically possible. They are not ruled out, but they are not yet supported by the kind of overwhelming evidence that would make them part of the standard picture. What we have, instead, is a set of observations that do not quite fit. The Eridanus Supervoid is too big. The KBC void is too deep. The Hubble tension is too persistent. The cold spot is too cold. The Hercules Corona Borealis Great Wall, if real, is too large. None of these, individually, breaks the standard model. All of them, together, make a quiet pattern that something more is going on at the largest scales than our current best theories predict. That is the deepest truth I can offer you tonight. The universe, where it is most empty, is also the place where our understanding starts to thin out. I want to bring us back, in the last section, to the place we started, one of the largest voids ever found, the Eridanus Supervoid, sitting almost 2 billion light-years across, in the southern sky, in the constellation of Eridanus. If you could travel there at any speed our current technology allows, you would not get there in any timescale that matters. Voyager 1, the fastest spacecraft humanity has ever launched, would take more than 30 trillion years to reach it, far longer than the current age of the universe. Even at the speed of light, the photons we're sending out today, in radio waves and infrared light, will not reach the center of the Eridanus Supervoid until 2 billion years from now. And by then, neither we nor any of our works will exist in any form recognizable to ourselves. The supervoid is not, in the practical sense, a place we can ever go. It is a place we can only see, and only barely. But the fact that we can see it at all, the fact that we have been able to build telescopes and surveys and statistical methods sensitive enough to detect a 30% underdensity in a region 1.8 billion light-years across, is itself remarkable. We have managed, from this small planet, to map the matter distribution of a region of the universe so vast that the human imagination almost cannot hold it. We have managed to align that map with a cold patch in the leftover light of the early universe, and to begin to tell a coherent physical story about how the two might be connected. That is not nothing. Think about what had to happen for us to know about the Eridanus Supervoid at all. Stars had to form. Planets had to coalesce. Life had to begin. Single-celled organisms had to evolve into multicellular ones. Multicellular organisms had to evolve into something that could think. Something that could think had to develop language, then mathematics, then physics, then telescopes, then satellites, then statistical inference techniques sophisticated enough to detect a small bias in the distribution of light from billions of distant galaxies. That entire chain of events, stretching from the formation of the first stars to a particular paper published by the Dark Energy Survey Collaboration in 2021, had to run all the way through. And at the end of it, we had a number. One of the largest underdensities we have ever found has a center about 2 billion light-years away, in the southern sky, in the constellation of Eridanus, and it is 1.8 billion light-years across. The supervoid, sitting there in the southern sky, is a kind of mirror. When we look at it, we see the limits of what our universe seems willing to provide. We see one of the largest empty things we know about. We see a place where matter is missing on a scale that our best theories do not fully predict. We see a region where the cosmic web has, for reasons we do not entirely understand, simply failed to weave. We also see ourselves, looking back. We see a species that has built the instruments and the patience to find such a thing. We see a civilization that has cared enough about the question of where we are, in the cosmos, to map the regions where we are not. We see, in the silence of the void, a reminder that the universe is mostly nothing, and that we are, in any meaningful sense, lucky to be here at all. The largest void ever found is so empty it should not exist. That was the title we started with tonight. I want to tell you, as we close, what I actually think that means now that we have walked through it together. It does not mean that voids are impossible. They are not. They are predicted, expected, observed, and well within the scope of normal cosmology. Almost everything we have walked through tonight, the Boötes Void, the Giant Void, the Eridanus Supervoid, even the KBC Void in which we may live, is consistent with the broad framework of the standard cosmological model. Our model produces voids. Our model expects them. What it means, instead, is that some specific voids are stranger than the model comfortably predicts. The Eridanus Supervoid is so large, so deep, and so well aligned with another anomaly in the cosmic microwave background that it has prompted serious discussion about whether our standard cosmological model is missing something. The KBC Void is so close, and so possibly connected to the Hubble tension, that it has become one of the leading proposals for resolving one of the deepest disagreements in modern measurement. The pattern, taken together, of giant voids and giant walls and persistent measurement disagreements is quietly pushing against the assumptions of the cosmological framework that has guided science for almost 100 years. The void exists, and it is genuinely enormous. The model that says it should not be quite this large or quite this deep is the part that needs adjusting. That is the honest version of the story. The universe is not broken. Our map of it is incomplete. Where it is most empty, our map runs out, and we are left with a question we cannot yet answer. I want to leave you with one final image, because it is the image that has stayed with me throughout the process of putting the story together. Imagine you are standing on a hill at night, looking up at the sky, in the southern hemisphere, in the direction of Eridanus. You cannot see the cold spot directly. The cosmic microwave background is too faint and too microwave for human eyes. You cannot see the Eridanus Supervoid directly. The matter that is missing from it is, by definition, not there to be seen. What you see, instead, is a region of the sky that looks much like any other, with stars in the foreground and the dim glow of distant galaxies behind them. But somewhere in that direction, behind the stars, behind the foreground galaxies, behind the dust and the cosmic web of our local neighborhood, there is a hole in the universe, a hole 1.8 billion light-years across, a hole so large that the standard model of cosmology has trouble fitting it into the picture, a hole so empty that the photons of the early universe lose energy crossing it and arrive at our detectors slightly cooler than they should be, a hole that connects somehow to the strangest cold patch in the leftover light of the Big Bang. That hole is there, behind the stars, while you stand on your hill and look up. The night sky has not told you about it. The constellation of Eridanus has not changed shape. The familiar patterns of stars and planets are still there, but the universe has a missing piece in that direction, and we have only just learned how to see it. We made the map. We followed it as far as it goes, and at the deepest empty place we have ever found, the map runs thin, and the universe asks us, very quietly, whether we are sure we know what we are looking at. How incredible is that? Good night.